start feeling uncomfortable with taping the whole thing. So if you keep not showing up, this won't happen anymore. Okay, not directed towards you, you're all here. All the other ones listening. Okay, so a couple of announcements. Appears that the room issues have been solved and the solution will be, but bear with me, I hope that this will actually occur. On Wednesdays, hours 7 and 8, we will be in auditorium 3. It's a couple of rooms from here. Auditorium 3 is big and has power outlets for, I think, almost everybody. So that'll work. And that means that the regular setup will change to this one. On Wednesdays, hours 5 and 6, we have a lecture. Hour 7 is Q&A. So I'll keep standing there waiting for questions as long as questions last. And on hour 8, we'll do the quiz. No likelihood that won't take a whole hour. And my guess is that it's going to be in auditorium 3 that is not implemented yet in OASE or OA Info or anywhere else, but make sure that you check whenever that happens, because it's likely to happen pretty soon. Then on Fridays we change the schedule to such an extent that, well, hour 1 is not a good idea. Hour 2 and sometimes 3 I'll lecture, and the time that we have left, so either both 3 and 4, or only 4, there's left to work on assignments, and I'll be in the room as well. Okay, so that's going to happen pretty soon, and as soon as it all has been officially resolved, I'll let you know once more through the forum so that you have it also in your email. But that's what we're aiming for. Okay, then I put a example Stata do file online in the module where it says this is our classroom data. It now says this is our classroom data and a Stata do file. Here V3 stands for version 3. That's my version 3. There will be updates over the coming weeks, and here you'll see the Stata commands that we covered, or at least most of the Stata commands that we covered, on our own data, so that you can get a feeling for what they are. Here, I know these from that distance you cannot read, but the point is not so much that you can read this. The point is that this is what the do file looks like when I type it, and what you should be able to see from the distance where you are now is that it is a sort of neatly arranged, not to say anal, in the sense that this is all lined out as much as possible. There's lots of comments in there, and I suggest that you follow that practice and create do files that sort of look like this. It's easy to create a do file and think while you're doing it, I'll remember what that is tomorrow, and then tomorrow you look at it and you have no clue what it was. I know from experience. So what you typically need is as much commenting as you can add to make sure that you understand also later on what it is that you did. So try to make sure that you do this in an orderly way. I've seen many students use all kinds of things together. So one thing you could do is, and you type a command interactively in Stata, then you put some code here, you block this, you run the blocked code, back to Stata again, something through the windows, and then, you know, after 15 minutes you're totally lost and you have no clue what's happening. So the basic thing to do is you create your do file. Whenever you add something to the do file, anywhere in the do file, then simply rerun the whole thing, because Stata is really fast, and as long as we have data like this, just a click on this play button over there will get you through the whole do file pretty fast. Okay, but anyhow, there's an example do file online, also with a couple of things in there that got less attention during the lectures. If statements after the command you will find here, have a look, and that will help you go through the data that we have ourselves. Okay, by the way, what I forgot to say, the Q&A hour is not to suggest that you cannot ask questions outside the Q&A hour, right? You know, if you have a question, we're all here, raise your hand and we'll be good to go. Okay, yeah, so this is a bit larger, perhaps a bit more readable. Check out these kinds of commands. This one for or, that one for and, if two conditions need to be fulfilled. This one, for instance, for creating a new variable, and all the regular commands apply. So times divided by plus minus raised to the power of, and so on. These, perhaps also of use, a star. So this is referring to all variables that are labeled feeling and then something behind it. So I think we have feeling 1 through feeling 14 or so. And all of these will be addressed here. So here you get a summary of all 14 feeling variables. And if you, for some reason, want only the ones that have one character behind it, then you type this feeling and then the question mark, and feeling 1 through 9 will be covered, which might be handy every once in a while as well. Another one that's good to have is this is your standard tag age, gives you all the values for age that you have in your data. And that one is tag age, comma, miss, explicitly show me the missings. Then you'll get an extra category in there, so all the age values and missing, and how many missings you have, which is handy every once in a while as well. Okay. Go through this by yourself, and you'll see that I think most or even all of the commands that we cover in class will be in there. It's now up to date, I think up and until t-test or so. So over time it will become longer. For instance, also with the ones of today included, then it will be called V4 and so on. Okay, so we're here. What we have already was, okay, Stata, got that. We're running on course. It's all about X's and Y's and how these are connected. We talked about hypothesis testing, H0s and alpha of 5%, and so on. Then we started with dealing with two categorical variables. For that you needed chi-squared and features exact. Then if you have a categorical variable, male, female, or whatever, with two categories and an interval variable, we know now how to deal with that. It's called a t-test. And if the t-test is not allowed, you can try something else. And finally, no, not finally, there will be more. But next is this one, two interval variables. That's called correlation. And it's related to what is called simple regression. I'll talk a little bit about what that is in a minute. And that will be basically the stuff that we'll deal with today. And we should be, well, we'll see how fast we are. First, these are the commands that we will cover. First one, this one is correlation, Spearman correlation, sort of a different version of it. reg for regress, to run a regression command. Scatter, to get a scatter plot. And predict e, comma, resid for residual. I'll talk about that later exactly what that is. These are the commands that we will cover today, at least the most important ones. Okay, this was in the survey. So this was the question: what do you know about the correlation coefficient? And we'll talk about that today. And half of you says, "Oh yeah, this is all well known." These are the top two categories. So that's good. Nevertheless, I'll go through it also for the other half. But you know, even the tough questions, I guess everybody should be. No, not everybody. Half of you should be able to answer. So we'll see how that goes. So let's see, what do we have? We don't have so many interval variables actually in our data. One is age. The other one is the estimate of net income. So we asked, what do you think that you will earn when you are 35, I think. That one's labeled net income. Then we had a soccer guess. That is, what do you think if you get 10 questions about soccer, how many questions will you have correct? And the soccer score, that is how many you actually had correct. And for all of these, you could argue that they are actually not really interval. Age is, in a way, closest. It's interval because, you know, the difference between 18 and 19 is really the same difference as between 22 and 23. So a difference of 1 is well defined. But for it to be really interval, what you actually need is that it can take on all values. Well, it can certainly not be below 0, or not above, let's say, 125. So it's not really interval in the strictest sense of the definition, but it's close enough. This one is already a bit more troublesome. Here we had, I think, 15 or so categories. So the first one was, what are you going to earn? Nothing to 500, 500 to 1,000, 1,000 to 1,500. So that is reasonably well defined as long as these interval values are identical. Well, that wasn't the case. The intervals got a little bit bigger along the line, so the differences are not really well defined. And again, below 0, there was no option to answer that. Also would be a bit of a weird answer. And let's say above, I don't know, 10,000 or so also was not a possible answer. So it's also not completely interval. Here it's sort of worse because the soccer guess is running from 0 to 10. The differences are well defined, but you know, 0 to 10, that's all there is, and below 0 or above 10 is not possible, and the same goes for the score, obviously. But these are typically, let's say, normally argued to be interval enough to do the calculations with. Let's create two new ones. One I already showed, I think, last time or the previous week. We have these items all about how happy you are, 17 of them, and we average them out. First, what we do is we have positive ones and negative ones. We flip around the negative ones, and then we average out the score that you have there. And we also have these sort of related to extroversion. And we had, what was it, 21 of those. So I keep in the background, I think a lot before I speak or act. I'm quiet around strangers, I'm interested in people. I take time out for others. These kind of things are all the typical things that you ask if you want to know about extroversion of people. There we did the same thing. The ones who are negatively phrased, we first turn around, and then we average out your score. And this was on a 1 to 5 scoring possibility, this on a 1 to 6. So in the end, you can, you know, if you score the lowest here, you have a 1, the highest you score a 5, and here is a 1 versus a 6. Here you see the, you don't see it, but if you browse through this at home, you'll see that the command here is alpha, and we'll talk more in a separate module about exactly what that is. So here you see it happening. It gives you two variables extra in the data. These two variables are interval scaled. One is called happy, and the other one is called extrovert. And they are coded in such a way that higher values are related to higher scores on that thing. So higher means you're happier, and higher means you are more extrovert. Okay, so that's an extra one that we have. The third one here, happy versus extrovert. And the questions here that we have is, okay, if you score high on the happiness scale, are you more of an extrovert? So this is sort of relating to the idea, oh, if you're really shy and introvert, does it also mean you're not happy in your own little place? That's sort of the question behind it. This is, do people in general have a reasonable guess as to how good they are in answering questions on a test on a given topic? And there, I'm not really sure what that is measuring, but this is suggesting something of the kind. The older you are, well, perhaps it's, the lower the guess. That would be my best hypothesis. You know, if it's far away from actually earning money, it's easy to keep up the image for yourself, I'm going to make a lot of money. And then the closer you get to actually having to do it, you start thinking, perhaps a little bit less. So if that's true, I don't know, but then you would find that with rising age, that guess would go down. Okay, so let's see. First thing to do, just to get an idea of the data, and we'll see later on in more detail how this can fool you if you don't do this, is look at the scatter plot. And the command in this data is scatter yx, and that will give you a plot. And here you see the three that we have here, the estimate on the vertical axis and age on the horizontal axis. Well, that doesn't look like much of a relation between the two. Here we see the number of correct answers on the vertical axis and the guess that people have. This looks like that there is a relation in it, sort of like this. And there we have, let's see, oh, I don't know which one is on which axis, but you know, let's say that that is extroversion, that is happiness, and there we see a bit clearer that there might be a relation between the two. Luckily, we do not have to rely on the fact that we're eyeballing all this. You can add this command behind it. So we have scatter yx and then two vertical bars on my keyboard, sort of on the right above the enter key. And then you type lfit for linear fit yx, and what you will get is the line in it. It doesn't look like this, actually. I put these in by hand, but you'll get a line there. And then you'll see here, okay, the best fitting line there is completely horizontal. So as age is increasing, on average, doesn't matter so much what you guess. So that whole idea about the older you get and the closer you are, okay, there's no support for that in the data. Here you do see, yes, if you are thinking that you are good at this, then more likely good you are. It's not completely correct, there are still quite a few mistakes there, but still it's a linear trend facing upwards to the right. And here something similar. You see that happiness and extroversion indeed seem to correlate at least a little bit. The slope is slightly upward. So this will tell you if there is a relation up front, a linear relation up front, at least loosely. Okay, so that's just by eyeballing the graphs, and we can do a little bit better than that. Yeah, one other example that I'll go through in a couple of minutes in more detail. We had the soccer data. There's a lot in there, but the easiest one would be height, how tall is a player, and weight, which should be an obvious relation there. The taller you are, the more you weigh, and this is what the scatter plot looks like for that. Here we have way more data points and the line that goes through it. And there are a couple of reasons why I wanted to show it. First, here you see let's say a typical nicely fitting relation. So this is a line and all the dots are relatively close to the line. The other thing is that you can imagine this was, I don't know exactly, but let's say a couple of hundred data points. If you have a data set with a couple of thousand data points, then browsing the plot is not helping you a lot anymore. You know, there will be dots all over the place. It will be one black blur of dots, and you can't see a thing. So this only helps if you have a data set that is not that big. So here we have weight in kilos and their height in centimeters. Okay, then, just for the ones who are into linear algebra, if I write this is actually not completely correct, or at least you have to know how to understand this. Height, this is a vector. In the data, in the spreadsheet, this is a long column, just like weight, a long column, and these are numbers. So what we're trying to do, and trying to predict the vector height from a vector weight, and I have two scalars with which I can do that. And then you can, if you really want to be precise about it, actually in front of this B0, there is a vector with all ones in it. Okay, so that's the linear algebra interpretation of this thing. Okay, so correlation, what is it? Half of you know this. It's the extent to which a straight line fits the scatter plot. If it fits well, correlation is high. If it doesn't fit so well, correlation is low. The typical letter for that is rho, or sometimes R. And the ones who are really, let's say, detailed about this would do this here. You use the Greek letters typically for the real rho in the population. And you use R for the correlation that you find in the data. Not everybody is as precise about this, but most of the ones who care about this a lot typically use the Greek letters only for the stuff that's happening in the population, and the other ones for the stuff that you're finding in your data. And the ones who really are into this Pearson product moment correlation coefficient. That is, let's say, the long version of what we normally call correlation. So if you find this, somebody has, in a paper, I calculated the Pearson product moment correlation coefficient. It's just this. Does the straight line fit a cloud of dots? Okay, so what does fit mean? Just to get a bit of an idea, let's start on the top left over there. Here we see a downward slope and 3 data points that exactly fit a line. Exactly fit means that rho is either +1 or -1, and the minus is only referring to the slope itself. So if it's sloping downward, it's minus. If it's sloping upward, it's a plus. So here you see, let's say, the equivalent there. This is a perfect fit. So rho equal to 1 and it's sloping upwards, and because of that it's a +1. The exact slope here doesn't matter. So 4 dots on a straight line like this, exactly on it, rho equal to 1. 4 dots on a line, again, rho equal to 1. So the exact slope, that doesn't matter. Here you see noise, rho is 0. Here, lines that fit reasonably well, but less good than perfect. So here you have a rho between -1 and 0. Here you have a rho that's positive, because it's sloping upward, but the line is not perfect. And let's say the better the fit is, the closer the rho will be to 1. So here you have, let's say, a rough idea of what the different values in between suggest. Close to -1, really good. Close to +1, also really good. And it gets more, let's say more hazy towards the middle part. Here, the thing I said a couple of seconds ago, this is just as good everywhere. So all these values these are all the same because they're all sloping downward. These are all the same because they're all sloping upward. And that's simply a 0. There is no relation. And then, also important, a correlation of 0 need not imply that there is no relation. It simply implies that there is no linear relation. So the best fitting straight line is horizontal. And for all these down here, you obviously see, yeah, there is a relation here. I can see it, it's not noise at all. There's structure in it. But the best fitting line for all of these is straight through the middle. So if you would have data like this, you would find for x and y correlation is 0. And you might conclude wrongly that there is no relation between the two. But the only thing that you can conclude is that there is no linear relation between the two. Okay. How is it calculated? If you're into formulas and into memorizing them, feel free. This is what they look like. Different kinds of ways to calculate it, and especially knowing these different kinds of ways. This was really important, let's say 20 years ago or so, when many of these correlation coefficients were calculated by hand. So then it's good to have. There's not a lot of intuition in it unless you know very well what correlation coefficients and variance and so on mean. Luckily, there are easier ways to understand exactly what we are measuring. So you have the formulas here. If you want them, you can use them or implement them or whatever you like to do with it. Especially this one is relatively easy to calculate as soon as you know, as soon as you've memorized exactly what that is. But the intuition is easier than that. So let's try to figure out what that is. We're fitting a line through a cloud of dots. And here you see that, a couple of dots over there. And apparently this is a straight line that fits best. Okay, so fits best. Best in what sense? Well, there we need something like this. What is a fit? And it's defined, let's say, in a vertical way. What we're measuring is these differences from the line. This one, that one, this one, that one, and so on. Because we have pluses and minuses, we don't want them to cancel out. So what we do is we square them, then we add them all up, and that sum of squares we want to minimize. So we have an idea of what is missing the data. We have observed data points. We model it through a straight line. We check how far away the model is from the observed. We square those and we add them all up. And that number we want to have as small as possible. And obviously, if you just would see the dots here, you would have an idea of, okay, the best fit would be something here, something over there, and certainly not something like this. But, behind the scenes, we have to really find what the actual best one is, and for that, we minimize the squares. Or we state it as that. So, this is another way to think about what correlation is. And that's related with what's called simple regression. You have one y variable, a target variable that you want to predict, with one x variable. And we're trying to find the line that fits the scatter plot best. And because of these least squares, it's called ordinary least squares. And you will see that is completely related to correlation. Let's go through the moves there. Yeah, first, here you see that, okay, this is the claim. This is a linear algebra problem, and the point that I'm trying to make here is that it is not related to statistics at all. You have dots, and you're trying to fit a straight line through a cloud of dots. The only thing that you need is being able to find what the best line is. There is no normality or probability or hypothesis or whatever. We're trying to fit a line through a cloud of dots, that's it. It's algebra, nothing else. It also has a closed form solution, so I could give you the formula. Actually right here, for what the best fit is. This is also why Stata is almost immediate in giving you the answer. There's just a formula behind the scenes that is being executed. And in Stata you do it through reg yx, regress y on x. And that will estimate what the line is that fits best. So here you have it, regress height on weight. So we're trying to use weight to predict height. and then you get a lot of stuff back. We'll go into details into what all these things mean over here, but I have to peek. Yes. For now, the only thing that we need is this here. There's a column called coefficient, and here you have weight. That's the variable that you have put over there. This is the constant, and this means that if we're aiming for the best fitting line, here you can see what it is. It is 125.78 plus 0.73 times weight. There's a lot more in here, but you know, if we're just aiming for the line, there it is. Okay, now, how well does it fit? So we can find already the definition of the line here, of the best fitting line, and how well does it fit. First one would be, let's say the worst model that you could think of, hardly a model at all, is I will predict whatever it is I'm predicting. Where was it, height or weight? Height. I want to predict height simply by the mean of the value of height in the data. So let's say that the mean of height is 1.78 meters. Okay, my guess is everybody is 1.78 meters. Not a very good guess, but it is a benchmark with which we can compare the rest. So that is what we see here. Okay, this is my best, let's say, base prediction. I'm just predicting the mean for all cases, and I'm calculating these squared differences, and I'm adding them all up. And you'll get a huge number, because that mean is, of course, not very good as a prediction. That's called the total sum of squares. So that is, let's say, how well I am doing, and that won't be very well, if the only thing that I use to predict is the mean. So now the question is, how much better do I get if I add the extra variables? So now I'm allowing here to find the line that fits best, and that will fit the data points indeed better than just the mean if you have a useful variable in there. And now again, I calculate these sums of squares, and now it's called the residual sum of squares. What I have left after I've included the variable there, that total sum should be less. This one is a really large number. A perfect fit would be no residual sum of squares. I've explained away everything. And here you already get better than there. And the question is, how much better do you get? So here we're talking about residual sum of squares and total sum of squares. And here you see in the table already there is something that's labeled residual, and there's something that's labeled total. And there you see SS, and that is sum of squares. So we have here, if we're predicting height with the mean only, then we will end up with a sum of squares that is this big. And if we're using the variable weight to predict, then we add it up to 50,381, whereas here we begun with 27,052. So indeed, we're getting better from all the things that we had to explain, that we had to get away with, 27,000 something. We're now having only 15,000 left. Okay, so that's better. Now, how well does the line fit? R squared, that's exactly that. So here we have the total sum of squares, the stuff that we need to explain away, and that we get by only using the mean as a predictor. It's a really big number. We hope that that big number decreases as much as possible if we add variables, here only one at a time. So now we're adding one of the variables to predict, and we again get a sum of squared residuals. If the line is now perfect, that sum of square residuals will be 0. And this thing on the right here will be 0, and my r squared will be 1. So the best that I can do with an r squared is 1. If it doesn't help, if I'm adding a variable, and that variable is not predicting my target at all, then I have a total sum of squares here. It won't get much better, so you'll have almost the same number over there. This thing will be 1, and 1 minus that will be close to 0. So the worst that you can do with an r squared is 0. You're not predicting anything. And the best that you can do with an r squared is 1. You can see it through this. So here, what was it? R squared equal to 1 minus, well, here we have that 27,000 again. And here, I think Let's see. Here we have 27,000. That's those. And then, oh, I see that I mentioned the wrong one. Should have focused on the residual one, of course. Here we have the residual sum of squares, 11,671, and 1 minus that thing is 0.5686, and that's right there. Okay, so these numbers over there are used to calculate the R squared over here. And we now find the value of, 0.57, which sounds reasonably good. Do you have a question? No? You solved it? Okay. Then, correlation, because it started with that. What is correlation? And it's exactly related to these R squared values, because the correlation between two variables, height and weight, here, that is the square root of the R squared. So here we have R squared, 0.57, and the square root of that is the correlation between two variables. You could also remember it as R squared. Yeah, R, what is R? R is the correlation between the two variables. Okay, so here and there I see people asking questions. Any questions about this? There's going on, if you're lost now, not good. Yes?
I don't really get what R squared tells you.
How well it fits. That's the thing. So if you want to, let's say, interpret that visually, how well a straight line goes through a cloud of dots. Where good is all the dots relatively close to the line, and bad is dots all over the place, and there is a line there, but it doesn't fit very well. And we're trying to calculate that, give a number to it, and that goes like this. Other questions? Okay. So here you have it, just to show you that this is actually true. Same table, R squared 0.57. If I type this, that's the command for correlation. Correlate height and weight. And here I find 0.754. And indeed, 0.754 times itself is 0.568, and that is again that R squared. So I'm not just saying this, but it's actually true. You can see it happen. So the new thing here is relatively straightforward. The command for correlation, CORR, and a couple of slides away, I'll show you that there is another command as well, PWCORR, where PW stands for piecewise or partwise. And as you see here, for two variables there is no difference. And I'll show you in a minute what the difference is if you have more than one variable to work with. Okay, so I've used this before actually. So I had a slide, I think in week 1 or lecture 2, I don't remember exactly, where there was some data about soccer. And one thing that people have done is they've tried to use salary to predict team performance in soccer. And it turns out that the R squared there is really good, an R squared of 0.92. So given that 1 is the best you can have, an R squared of 0.92 is great. So apparently it is the case that you can predict the actual performance of a soccer team very well, simply from adding up all the salaries that the 11 players have. And also that what you could do basically in the same way is if you do not add up the salaries, but you add up the transfer sums, so what has the club played for that particular player, that is a predictor as well, but much worse. Then R squared is only 0.16. That's getting closer to 0, where 0 is nothing. Okay, then now we're going to complicate matters, because I was trying to make the point, the slope of the thing is not related to how large the R squared is. The only thing that matters is how well the line is fitting the cloud of dots, and the rest is doesn't matter. And here we'll see that there nevertheless is a relation between the two. And for that I need a bit of a run. First, this was something we've seen a couple times. Standard normal. Okay, a hump, the 0 in the middle, and if it's standard normal with a mean of 0 and a deviation of 1, and it looks like this, we have that almost all the data points lie between -3 standard deviations in that direction, +3 standard deviations in that direction, and there's only a little bit on the edges over there. Okay, so this is a standard normal distribution. You've seen that a couple times. Now, what is standardization? Standardization is if I have a variable and I subtract from that variable its mean, and then I divide through its standard deviation. It looks like this. I have a variable x, I subtract the mean, mu, and I divide by the standard deviation. Now what will have happened? If I subtract the mean, first I had a variable that had a mean mu, I subtract it, now I get a variable with a mean 0. So the new variable will be centered around 0. The second thing, if I divide by the standard deviation, then the original one had a standard deviation, sigma. If I divide by it, the new one will have a standard deviation of 1. So that will, if the variable itself was normal, this will ensure that you get a variable that looks like this. The 0 there, -3 standard deviations over there, +3 standard deviations over there. If you have something that is not normal, then this does nothing to the shape to make it more normal, but what you do get is the mean is 0 and the standard deviation is 1. Now, we have a command for that in Stata. You don't have to do this by hand. You could, by the way, so if you have a variable where you can see the mean is 5.2 and the standard deviation is 1.3, you could create a new one, x standardized equal to the original one minus 5.2 divided by 1.3. That would work. The easier thing to do would be to use this one. This is a bit of a nasty thing that you have to memorize.Egen for extensions to generate. Not exactly sure why they do that. X standardized, that's something that you dream up yourself, and then standardize X. That will do the same. Okay, now, why do we need this? Because here you have, again, the regression of height and weight. Same thing, again, that r squared of 0.57, and the best fitting line, nothing new. Now we do the standardization bit, so we had height and weight. They have means and standard deviations. I create two new variables, standardized height and standardized weight. And you'll see indeed here, this was the mean for height, 180, and this is now the mean for height, which is, yeah, this is 0. 10 raised to the power of -9, so that's not a lot. Same thing here. And you'll see that the minimum is, let's say, -3 and +3. Here also -3, and well, this one actually has a value of 3.8. But you see that, let's say, the scale of this variable is indeed as you would want it. 0 here, a 1 there for the standard deviation, and roughly all cases between -3 and +3. All right, why is that of importance? Now, same regression here on top. Now I have a regression here, the same one, but now on the standardized variables. Standardized height and standardized weight. And now what we get here is, first of all, nothing new over there. All this is exactly the same as there in terms of r squared. But here we get the coefficient for the slope. This was representing the slope. And that thing is exactly, and not coincidentally, also what the correlation coefficient was. Okay, so this is where the confusion hits in. I started with correlation is how well the line fits. And if it fits well like this, you get a correlation of, let's say, 0.5. If it fits just as well like that, you get a correlation of 0.5, and the slope doesn't matter. Okay, with this whole regression thing, we're measuring the slope. And if we standardize both variables that we have, then we'll see that the slope is exactly correlation coefficient. There is a relation between the two. That's a bit of a nasty one because you can easily mix it up. So one way to memorize what a correlation coefficient is it is the slope of the regression line of the two standardized variables. Also true. Okay. Yeah. There it is. Same. Now, so this is basically what we need to know to calculate the correlations and the simple regressions. Let's see what happens here with age and net income, with soccer guess and soccer score, and happy and extrovert. First, some data fumbling. For net income, we had categories, 15 of them. And actually, I would like to relabel those, because in the data they are coded like this, from 1 all the way up to 15. But 1 is representing a given category that has a beginning and an end. And what I'm trying to do here, I'm trying to replace these categories with the midpoint of the two ends. So here, if you have 1, that is saying something like, you think your salary will be between 0 and 1,000. Here, 2, you think your salary is going to be between 1,000 and 1,500. So I'll put the midpoint 1,250 in there. And this is the way in which you do it. You create a new variable, income estimate equal to net income. I replace all the way here for all 15 categories, and here I added a label to it. I think this is also in the example GRU file that is online. So actually this is a better way to do it, because these are actually the numbers that you gave, and these are only the numbers that you get back from your survey program. 15 categories, but they, let's say, have a different meaning than this. So for instance, there, this is 15,000. This is off the charts. If you think that you're going to be a millionaire, then you're somewhere over there. And that difference here is only 1, whereas the difference that you have answered is actually bigger. Okay, so we're changing from net income to another variable that's called income estimate. And that also makes a difference. Just to make that clear, here we have correlation. Close to nothing, so there is no relation, in our case, between age and that estimate. Here we have regression, income estimate on age, and here we see a coefficient of, let's say, -5. By the way, you see the same R squared, close to nothing. And there we have net income, that's the original variable, and age over there, and you'll see that the coefficient is slightly different. Or a lot different, whatever you like to call it. Okay, in this case, there was no real correlation, so the model is not fitting very well, which you can see from these really low R-squared values. So here we're toying with noise, basically, there is no relation. But at least what you see here is it makes a difference how you code the variable. This is exactly also what you want, because the correlation is attempting to pick up exactly what the relation is. So if you move them around a little bit, I had 15 categories, and now spreading them out to some extent, and here less than there, you'll get different values in the end. Okay, anyhow, no relation between these two variables. Soccer score and soccer guess, you see both the means of doing this, 0.46, we had that already, there is a relation there. We have here an estimate of a coefficient of 0.25, so the best fitting line here is 3 plus 0.25 times soccer guess to get your soccer score. R squared of 0.21. 0.21 is exactly the square of that number. And the same thing for happy and extrovert. Actually, this is the largest correlation that we find, 0.57. The square of that is 0.32. And the best fitting line is 0.63 plus 0.73 times the score you had on the extrovert scale. And this, for instance, could mean that if you know that this is the case, then instead of having to measure, 14 items for happiness and 17 items for extroversion, you might argue, well, let's forget about that, because if I have extroversion, then I can predict reasonably well what you would score on the happiness scale. And there is no need to ask for these 14 different items. Okay, let's see where we are. Yeah, then one last thing before the break. Here you see what the difference between correlation and piecewise or partwise correlation is. After the correlation command, you can simply make a really long list of all the variables that you want to look at. And what you'll get back is the correlation between all variables. So here you see correlation of age, the income estimate, the soccer score, the soccer guess, happy and extrovert. So basically all the things that we had. You see them here, and you see them there. And here you see the 0.45 that we had for soccer guess and soccer score, 0.56 that we had for happy and extroversion, and so on, and all the other ones as well, and many of them relatively small. And you see here that if you do the same thing, piecewise or partwise correlation, and then the same list of variables, then you also get numbers like that, but they are slightly different. Here you see 0.4587, 0.4531, and what's happening is this. Here, the correlation is calculated on all cases that exist in the data for all variables. So it might be that, and here we have it, let's see, for the income estimate we have 142, that's the least of this list. So there are a couple of cases, 9 of them, where we don't have that estimate. So these 9 are not included in the calculation of the correlations for all of them. So for the correlation between age and, let's say, happiness, I have 151 cases, and I could use all 151 of them. But here, I don't. I only calculate on the smallest subset for which I have all the variables. So this is calculated on 140. There is another missing here and there as well. And this is calculated on the largest number of cases that I can use. If I calculate here the correlation between age and happiness, where I have 155, age and happiness, it's that one. That one's calculated based on 151 cases and not on 140. Okay. As you can see here, in this case, it doesn't matter so much. We're only losing a couple of cases. But if there is a variable in here that has lots of missings, and for instance, if you ask in a survey for an estimate of income, a lot of people won't give it. 1/3 or so of your respondents will refuse to give that number. Then you'll find that if you do this, all correlations will be calculated only on the 2/3 of people who actually answered also the question on income. Okay. Quarter 2, I'll continue.
R squared being 1 minus something. Is that any different from the statistics class? No, but apparently, as I understood it, there they explained R squared in a slightly different way. I use 1 minus this over that, and of course, you see that number here and there. What you could also use exactly the same is that one divided by that one. And I think that in the, if I understood it correctly, in the statistics course, this is called the regression sum of squares, and that is the total sum of squares. And that would be exactly the same number. So there is no light whatsoever between what's being taught in the statistics course. It's not that here a 1 is low and there a 1 is high, or none of that. So a 1, closer to 1 is better. Here and everywhere. Okay, where were we? Yeah, this is where we stopped. So we did the correlation, we did the best fitting straight line, but there was no statistics involved just yet. So what about the hypothesis testing and significances and so on? And indeed, we still need that. It's relatively easily done though. So this is what it looks like. Here we again have that correlation command, now with the PW in front of it, so partwise correlation. Correlation between all the variables that you have there, all 6 that you have, and the only thing extra there is this thing, sig or significance. Show me statistical significances. And then what you get is, as an extra, here, first the correlation between the 2 variables, between age and the income estimate, and their significance test. So, significance test, again, what's the first thing to figure out is what is H0 in the significance test. H0 is, there is no relation between the 2 variables. So what was being calculated behind the scenes is, if it would be true that these 2 variables are not correlated at all, how likely would it then be to get data of this kind? Okay, so you have here 0.94, way above 0.05. So here we do not refute H0, and in the orange underlined cases, we have values smaller than 0.05. This one is as close, but still smaller than 0.05. So there we refute H0. So for instance, this one, no, let's take another one. The soccer estimate
sorry, the soccer score and the soccer guess, the correlation was 0.46. Here we see significance way smaller than 0.05, so we refute H0 that there is no relation between the two. Or same thing there, also there by the way. So for one reason or another, there is a significant correlation between your soccer guess and how happy you are. Not really sure. Well, one argument would be if you're happy, that's correlating with being optimistic. So if you ask somebody who's happy and optimistic, how well do you think we're doing? They are more likely to be more positive than the ones who are not so happy. And there is some evidence for that, because there is a correlation between the two. It's 0.16, and we can refute here, borderline, but nevertheless, that there is no relation between the two. Let's see. To see that there is a, let's say, a real relation, a significant relation between the two variables, you could also see that in the same regression table over here. So here we have it, soccer score predicted by soccer guess, and happy by being an extrovert. Here we have the coefficient. If I want to predict soccer score from soccer guess, what I do is for every extra value of soccer guess, I add 0.25 to the soccer score. And here you see the P for probability. So here you see this value smaller than 0.05, way smaller than 0.05. So we can refute H0, and H0 would be this coefficient over there is actually 0. And apparently it's not. We refute that. Same thing here. The hypothesis is this coefficient. If that would be 0, how likely would it be to get the data that we have? Not very likely. Yes?
Why is your H0 that the coefficient is 0?
Yeah, there is no reason why that should be H0, but it is. You know, as long as I have an H0, I can run the calculation. Or say I can run the calculation to this. So we might want to test here, let's say, is this coefficient 0.25, 4.5? And we can, and we will later on, but by definition, by default, what you get back is the hypothesis test on H0, where the coefficient is non-existent. But you're right, if you would have another H0, then the test would be slightly different, but you could do the test as well. And we will later on. Okay, so a little bit extra in red. We already had correlations, the extent to which a straight line fits the XY scatter plot. It's called rho or R. It's called the Pearson product moment correlation coefficient, all the same thing. And it also is the extent to which knowing X would be of use in predicting Y using a linear relation. And the using a linear relation is crucial. Okay, there are a couple of things to remember, because this is all relatively, I hope, relatively straightforward and at least close to the statistics class as well. So here we go. First, this is relatively speaking still the easy bit. Here we have once more regression of weight on height. Here you see the coefficient 0.78 and there the constant minus 65.85. And that means, okay, if I want to predict weight from height, then this is the best straight line. This is the formula for the best straight line. And that means, as a sort of a literal interpretation, for every 10 centimeters that somebody is taller, you add on average 7.8 kilos. So, and by looking at in this way at the coefficient, you get a feeling for what's going on. Okay, 10 centimeters taller, 8 kilos extra, roughly. Or what you could also do is, if these would have been standardized, we saw that a couple of slides ago, then you get a different kind of estimate for the coefficient, then it's 0.754. You could also interpret that. That would mean for every standard deviation to the right for the height variable, you go 0.75 of a standard deviation to the right in the weight variable. And if you know up front that, let's say, the whole of the variable is between minus 3 standard deviations and plus 3 standard deviations, that also gives you sort of a feeling for how big the effect is.
So this is the direct interpretation of the straight line. Okay. Now, I already got the question during the break. Tell me how high should that R squared be? And when is it good? And I also heard from, who was that? The guy from the statistics slides, that said, yeah, above 0.7, that's a good model. And below, it's not. Who was that? Where are you? Yeah, did they really claim that? As... Oh, okay. I think that's a lot of bull. That's all not true. I'll try to convince you why. So I was in sync with the statistics class up to now, but here we start to deviate. Okay, first the big thing is that predicting and understanding are not the same thing. I've collected some data. This is from the, I think the AEX. I don't know which dates, but you know, I have a couple of data points, 20 data points of the AEX. And what I use is a model where I predict what the AEX is going to be simply by what it is today. So I have no clue how all that works with stocks and who knows what. I know nothing about the market, but I do know that tomorrow's AEX score will be roughly the same as it is today. So a slight deviation. If you do that, you get something that looks like this. I put this in a scatter plot, and I get a straight line that fits reasonably well. I can do the regression. It's really small over there, but what you get is a correlation of 0.53, or an R squared of 0.25. What is it? Yeah, a bit more, 0.28. So that's not so bad. So that correlation here already is quite large, you could argue. It's not up to the level of the 0.7 that apparently the statistics class they need. But what I've done here is I've come up with a reasonably well-fitting model without knowing anything. I'm understanding nothing. And still I get a prediction that's really good. So getting a high R squared in itself says nothing about whether or not you've understood what's going on. And here, of course, you could argue, who cares? If it works, and I know what tomorrow's stock market is going to be, even though I do not really understand why it's working, I don't care about that. I'm making money of it, so that's the whole, or the only thing that I want. That could be, but that in itself doesn't mean that you have a decent model if you want to understand what's going on. So just saying R squared is large is not enough. Another example, this is weather data that I don't know, I got this from the internet somewhere, where the same argument applies. So I'm trying to predict, I think, average temperature on a given day. Now, I have no clue about meteorology or what have you, but I do know that tomorrow, roughly, it will be the same weather as today. So I'm predicting tomorrow's average temperature by today's average temperature, and that actually does very well. I now have a correlation of 0.7. Oh, this is close to the statistics class already. And that would mean, if I do this, I've calculated my regression model. After I've calculated my regression model, what I do is I predict a new variable. I'm going to call it E. And what it's supposed to be is the residual. It's the extent to which I miss from my target. Now here you see an overview of what I then get, and you'll see that, let's say, this will give me predictions, almost all of which are between -4 degrees and +4 degrees of the actual number. So if that would be good enough for practical purposes, then without knowing anything about the weather, I'm able to predict it for tomorrow simply by saying, tomorrow it's going to be about the same as today. This is also why it's really tough, if you are the weatherman, to come up with, let's say, added value over yesterday's weather. Okay, so in principle, I think I would be a pretty decent weatherman just by predicting for tomorrow what it was today. Correlation of 0.7, roughly. Every once in a while I would be wrong, but the true weather person has to do better than that 0.7 already and needs extra information to get at 0.8 or 0.9. Actually, it's not so easy. So in the weather predictions for tomorrow, we are now really, let's say, on the edges, trying to improve from a 0.84 to a 0.85, nothing of which anybody will ever have, notice. So again here, quite a decent model in terms of prediction, quite a bad model in terms of understanding, because we haven't understood anything other than that there is seasonality in it. Tomorrow will be like today, in all likelihood. So what are these typical correlation coefficient sizes in the kind of, well, psychological research or in general social science research? We're measuring humans and we are comparing the different things that we measure. You find around 0.1 is typically called a small effect size.
So a small effect. Around 0.3, a medium effect size, and around 0.5, it starts to be large. I think the big bulk of the studies, let's say 50 or 60 years ago, in psychological research, there you can still hope to find a lot of large effects, because not a lot was measured yet. So there is a lot to measure that you can hope to find as soon as you do it. Nowadays, there's a lot has been measured already, and we see typically this. About a third finds effects smaller than 0.2. About a third between 0.2 and 0.3, and about a third above 0.3. So, you know, if you're only satisfied with models with R-squareds above 0.7, then none of these will work very well. But nevertheless, this doesn't mean that these models are not useful. It's just implying that you shouldn't use them to actually predict. Okay, so no general rule for that. Don't ask me how high should it be. First, small correlation sizes need not be unimportant. We know, for instance, here that the effect of aspirin on the probability of a heart attack is about an R of 0.03, which is close to nothing. And nevertheless, this has influenced policymaking. So these aspirins, they don't help much, but they help enough to make it worth swallowing it if you if you want to make sure that you don't get a heart attack. On the other hand, if understanding is what's going on, and it's also here for this R equal to 0.03, then it might be important that there is a relation between the two, however small it is, just to understand, yeah, it does make a difference. If X is increasing, whatever it is, then Y is increasing. Maybe not a lot, but there is an effect there. And whether or not it is interesting, yeah, you'll have to figure out from the actual thing that you were studying. For the weather, perhaps, you want bigger values. For medicine, smaller values might do as well. And what we also see is that these high correlation sizes in themselves are not necessarily correct or the models to look for, because we need not be able to understand anything even though we have a high correlation size. By the way, if you are calculating on our own data, so this is all behavioral data on humans, and now you've created a couple of variables and are fumbling around, and boom, you run a regression, and now you find an R-squared of 0.93 or 0.95 or even 0.99. In all likelihood, this means that you've done something wrong. There are no models, I think, on the data that we have that have such high R-squareds. And one thing that you could have done is accidentally, in your target variable, there's something that you have called Y, and in your X variable, you have created something where that Y is also in there somehow. You don't know exactly what you've done there, but if you do that, then you get an R-squared that is really high. So for now, if you're calculating on social science data, you get R-squareds above 0.9, don't be happy about this. In all likelihood, you've done something wrong. Okay, then, just to show you what you from statistics class might remember, if you change the measurement of the variables, but in a non-substantial way, for instance here, once more, regression of height and weight, coefficient here, 0.73, R-squared there, 0.57. Now we create a new value over here. We have weight in kilos, but let's suppose that we're now measuring in Dutch ponden. So now we're creating weight times 2 and call it half kilos. So we now have measured weight in half kilos. Nothing has changed, only we have changed the numbers a bit, but substantially nothing has changed. What you see here is the coefficient itself is cut in half now. This is exactly half of that one. But the R-squared, as you would have hoped, is exactly the same. R-squared is only about how well does the line fit the cloud of dots, and is not dependent on how you measure it, as long as you transform linearly. Okay, the scatter plot changes too. This is interesting to see because this is height by kilos and this is height by half kilos. So if you just go by the scatter plots to judge how high the R-squared would be, you would be tempted to think here that this one is a bit worse than that one. But it's not.
all the more reason not to go by the scatter plot only. You know, the scatter plot is useful to see is there something of a structure in there, or there's a cloud of dots like this, going up and then going down, or having some other kind of particular shape. But to estimate the correlation from, you know, you have to be careful there. There's also no need to do it because you can simply do the math and the data will show. Then something else that is weird if you think about it, and even if you think about it for a while, it's hard to grasp intuitively. If you regress height on weight, once more, same thing, this gives you a regression line. You could also regress weight on height, so just the other way around. And you might think that that in principle gives you the same thing. So, yeah, there. So we have height on weight, that's the regression line we're going to get. This is the coefficient again, and the constant. If I rewrite this, I get that. Weight equal to this. Okay, just algebra. So now you might think that if I now regress not height on weight, but weight on height, that I should get this. The same thing that I got over there. But that's not the case. If you do it, you get this. Which is kind of weird. So it makes a difference if you run the regression one way or the other. And the reason is, it's sort of in here. We're calculating best fit based on vertical distance. And what is best fit based on vertical distance need not be best fit based on horizontal distance. And if we swap x and y, that's actually what we do. So if this is what we're minimizing, the sum of squares in the vertical direction, that need not be the same as the sum of squares in the horizontal direction. And this is why regression of y on x gives you a different line than a regression of x on y, or at least can give you a different line. Very often there is a sort of an obvious way which one to put on the left and which one to put on the right. Not in this case, but typically what you want is you want one variable to predict another one, and if the one that you want to predict is typically the y, you put it in front, and the one with which you want to predict is typically the x, and you put it to the right. Okay, then in statistics class as well, they must have mentioned a couple times that correlation and causation is not the same, or not even related. Yeah, so it doesn't mean, let's get here, by definition that, you know, that the first is weight and then you get height or something. It's not that you first get happy, and if you're happy you get to be an extrovert, or the other way around. It's just that there is a relation between the two, nothing else. Okay, one side step. We talked about interval variables all the time. An interval is, okay, the differences are well defined. There was another group of variables where we, yeah, I think I said, well, we will not encounter those very much, but every once in a while we do. And that's the variables that are ordinal. So there is an order in there, but the difference between the categories need not be exact. And you could have this, for instance, in the question of better than average. We've asked how do you compare to the average? Way worse than the average in my group, a bit worse than the average in my group, about average, a bit better, or a lot better. And the difference between a lot better and a bit better, it's not obvious that that is the same as the difference between a bit better and average. So there, what you do know is that there is order in there, but you do not know much about what the actual distance is. And the other one is, let's say, what was it? Do you play soccer? I think this one is no, that one is sometimes, and that one is never. Or the other way around. I don't remember. And in any case, there's an order in these three. So now I have two variables. These are ordered, but I have no real interval scale. And for that, we can calculate a correlation coefficient as well. It's called Spearman's correlation. And what Spearman actually did was relatively straightforward. It first calculates the ranks for both variables, and then a standard Pearson correlation coefficient between the two. And here you have it, let's say 0.04 between these variables, so close to nothing. And you get a significance test immediately afterwards as well. H0 is, once again, these two variables are independent, and what we're testing is how likely would it be, if indeed these two variables are independent, that we get data as we have.
and it has a value over there way more than 0.05. So we're not rejecting H0. H0 here is supported. The data that we get could very well be caused by the fact that play soccer and better than average are not related at all. Okay, so we also have correlation now for variables that are not exactly interval. Then, yeah, now I mentioned first look at the scatter plot, then don't look at the scatter plot for the exact number. But there are quite a few well-known examples where it at least pays up front to see if there is some kind of shape in the scatter plot, just to figure out what's going on. This is what's called the Anscombe data. The Anscombe data consists of 8 variables, 4 x-y pairs, x1 and y1, x2 and y2, x3 and y3, and x4 and y4. And you see here that, if you look at this from a distance, they're all the same. x1, 11 observations with a mean 9 and a standard deviation of 3 and a bit. Same for x2, same for x3, same for x4. Y, 11 observations, mean of 7.5, standard deviation of a bit more than 2. So it looks like, x1 and y1 are interchangeable with x2 and y2, and so on. Also, if you calculate the correlations, you get 0.816 and a bit for all pairs x1, y1, x2, y2, and x3, y3, and so on. So you could think, okay, all this is exactly the same for all the standard things that we calculate. But the Anscombe data is made to cause this exactly because this is what the data looks like. Here we have x1 and y1, goes like this. Here we have x2 and y2, goes like that. So there is a relation there, but it doesn't look very linear. Here we have x3 and y3. There is a very good linear relationship, except for that thing over there. And here we have x4 and y4. There is something weird over here and a separate case over there. So all these have similar, let's say, default statistics, mean, standard deviations, and correlations. But if you look at the data, then you would immediately see what's going on. This is what we see most of the time. Here you should figure out, aha, there might be a linear relation here as well, but I should better fit something that is not linear, for instance, a parabola. We'll talk later about exactly how to do that. Here you should consider, okay, these are so well aligned, what the heck is going on here? Is that a data or a coding error of some kind? And here you should, again, figure out, okay, there's a weird case over there. Why is this case over there? Is that really a true case, or did I simply make a mistake here? Okay, so looking at the plot is useful to figure out these kind of things. It also shows that correlation is relatively sensitive to outliers. If you have a couple of weird outliers, this will change the correlation value. Here you would have a perfect fit, so an r squared of 1. Now the line looks much worse, given that we have to include that point. Same thing for the other one. Okay, one more rule of thumb. We had the 1 over square root n rule already. There is more with over square root n. If you want to guess just from a distance while reading a paper, for instance, when a correlation coefficient will be statistically significantly different from 0, this is the rule. The correlation coefficient itself should be bigger than 2 over the square root of n, where n is the sample size that's being used. So n equal to 100, square root of 100 is 10. So all correlation coefficients bigger than 0.2 will show up as statistically significant if you have a sample size that is at least 100. Now that in itself is useful to check if somebody has done their calculations right in a paper that somebody else is writing. But it also shows something that is really important. It's also showing that if n is large enough, if you have a really, really big sample size, then any correlation, however small, will turn out to be statistically significant. So R is 0.003, as we had in the aspirin example, so it's close to nothing. Okay, if my n is big enough, I don't know exactly how big, but thousands, then this equation will be fulfilled, and I will find that even a coefficient of 0.03 is statistically significant. Another way to understand that, by the way, is that suppose that we're that we have a population and we have sampled from that population, and we need the statistics and the statistical significance to figure out what is going on in the population as a whole. Now, if my sample is small, we have to figure out what's going on, basically the way in which we did this. But let's suppose that the sample is close to the real population. Then it is really likely that you will find a significant effect. If in a very big group, let's say the difference between males and females is really, really small, 50 versus 50.0001. If your sample size is big enough, even that will show up statistically significant. So finding that something is statistically significant, that in itself says nothing about whether or not it is substantively interesting. So we're trying to figure out, is there any difference on the happiness score between males and females? And we do a large sample, and we find, males score 5.2, and females score 5.2000001. If our sample is big enough, we'll find, there is a statistically significant difference. But it's so small, who cares? So this is one risk with big samples. Everything in the end will be significant, and it means nothing. Okay, so this is where we were. We had correlation through CORR, or partwise CORR, to calculate it. It's all about how well a straight line fits a cloud of dots. If it fits well, you get correlation values that are high. There is a relation between simple regression, it's in fact what's happening behind the scenes, and how well the line fits. Stata is actually calculating the line that fits best, and then figuring out how well it is fitting. There is a sort of a weird relation between standardization of variables, you see over there, and the correlation coefficient. We saw that. Prediction and understanding are certainly not the same, so the R squared bigger than 0.7, forget it. First of all, we will never find R squared, in all likelihood, never find R squares that are that big, and let's say R squareds of 0.1 are decent and tell you something as well. If you want to calculate correlations on something that's not exactly interval, but there is order in it, fine, that can be done too. It's called Spearman's rho. So instead of the standard rho that we use for correlation, Spearman's rho is what you use for ordered variables. You can test it for significance. Is it different from zero, that correlation? And in response to the question, you could also test, is it different from another value? We'll show later how that works. That's possible too. But again, the same kind of hypothesis testing is going on here. You have an H0, you test against it, and in the end, if the value is smaller than 0.05, fine, you refute H0, bigger than 0.05, H0 is supported. And, perhaps even the most important thing, statistical significance, that in itself says nothing about whether or not the finding is substantively interesting. If it's substantively interesting, that comes from you understanding what the data is about, not so much from the statistics. Okay, that means from the single XY combinations that we had, there's only one left, and that is where we have a categorical variable with more than two categories, and one that's interval. And I see people dozing off. The guy over there, you also, you already came in late. So it's not a good idea, I think, to continue this. So for this, there is a module online where there is